Okay. Hello, everyone. So today, Joanna will be teaching me about all I know is it's something to do with Infinity One categories, maybe related to your recent work. So Joanna's just joined us as a postdoc at the UK office, and I'm interested to hear a bit about what you're interested in.
Thank you for the invitation. Nice to meet you and everybody else in Toppers Institute. And today I would like to discuss with you on my previous work
Hmm.
about Infinity One categories with structure and their logarithms.
Okay.
So, first of all, I would like to talk about how my project was motivated. So, indeed, there is a theorem by Hu and Ferretti, which states that for a quasi-category with J-shaped limit, so which means for a simplicial set J, um, A has J-shaped limit.
Hmm. Sorry for a simplicial set A with some inner horn lifting.
Yeah,
Yeah, okay. Okay.
quasi-category,
Okay.
inventing one category.
Okay.
Yeah, one kind of model.
Hmm.
Yeah. And
And so
then
is J like another quasi-category, which is the
simplicial set.
okay. Oh, just a simplicial set.
Yeah,
Okay.
yeah. And then let T be a monad on A. So you can think of it as from A to A. So
Hmm.
just like ordinary category theory,
Okay.
which does not preserve those limits.
Hmm.
Then the Eilenberg-Moore objects, or say the quasi category of algebras, still admit limits.
Okay. So even if T does not preserve the J
Yeah.
limits, the Eilenberg-Moore category still has those limits. Okay. So I guess is that surprising? Like all Eilenberg-Moore, like if we think just for one categories, if we got a monad on a one category, I always get for free that the projection from algebras down to the original category creates all limits.
Yeah.
And so if I've got limits in the downstairs category, I get them upstairs, regardless of whether the monad preserves them. Okay, so this sort of this is this seems like something which is true in the one category case I'm familiar with, so maybe not too surprising in the infinity one category case. So I do have some questions about so I think in general, I might have to like constantly interrupt you to try and like match match this with like the one category
Yeah.
definitions I'm familiar with. So we've got a monad on A as a quasi category. So I don't know the formal definition of a monad, but is
Yeah.
an Eilenberg-Moore object. So is there how do I is there some quick way you can like tell me how these things that like is there a two category or a bi-category of quasi-categories I can like
Yeah.
imagine these in or
So first of all, let's talk about the monad.
okay.
So uh, it's just very much like the ordinary case.
Hmm.
So we know that uh, there is a two category of a free adjunction, right?
Hmm.
So there's like two, it's freely generated by two objects, which people denote by plus and minus,
Hmm.
and two morphisms, two one morphisms, F and U.
Yeah,
Sorry.
yeah.
I speak the words that I'm
Yeah.
writing. And also two morphisms, which we would like to think of them as the unit and co-unit.
Hmm.
satisfying the triangle identity.
Yeah.
And so then we can look at the full subcategory of H
Hmm.
and D.
Right. Is that just the one at the point
Yes, the
plus?
plus, yes,
Okay.
sure. And this will give us a two category of like a free monad.
Okay.
So like because it will look like something like this.
And that so that'll be the delooping of delta plus, right? Is that
Yeah,
yeah.
exactly. We have this is eta and this is yeah,
Right,
something
right,
like
okay.
eta composing with other stuff.
Hmm.
Yeah. And then I a monad can be considered as a functor from MND
Uh,
to QCAT
so
quantum
there's some
category.
two, is this a two category or a bi-category
Mm.
quasi-cat or?
We can view a two category as a simplicial category.
Uh-huh.
Yeah.
By taking the nerve on all the home
Yeah,
categories?
yeah,
Okay.
yeah, yeah. So
Okay.
that's the idea.
So I view so monad I know monad as a two category, but you're
Yeah,
saying we think of it as a simplicial category
yeah,
and quasi category is a simplicial category
yeah,
as well. Okay. Okay.
yeah. And that's how a monad is defined.
Right.
And for Eilenberg-Moore objects, we can express them at weighted limits,
Mm-hmm.
but also there is a more diagrammatical or more like intuitive
Mm-hmm.
uh, description. So in ordinary category theory, so if you have a monad on A, then we can build the Eilenberg-Moore objects out of A by first considering the inserter
Mm-hmm.
of something.
Okay, yeah.
Like I remember T, you have the monad T and the identity, which because you would like to get, well, say, let's imagine that A is a category, then we have an object, small a. In
Mm-hmm.
A, because we want something like this, the structure morphism.
Yeah.
So we can build an inserter to like input those structure morphisms.
Right. So we've got
Yeah.
maybe like so oh okay. So we've got a monad. So like morally I know that like you would this would be an instance of like
Yeah.
taking an inserter for these two things. Right, but this picture is this
Uh,
the idea or what's
yeah, usually it's like that.
yeah, okay. So you get
Yeah,
some two cell
yeah,
filling that picture.
yeah, like that.
Um so is this and is that sort of formally what we're doing here? So we've got this
Yeah,
map from monad into quasi cat, which picks out plus maps to A, and then we
yeah,
get some morphism. Okay, okay.
yeah,
Oh,
yeah,
sure, sure, sure. So this is like in the Hom simplicial set from A to itself.
yeah.
There's a one cell corresponding to um corresponding to UF and
Yes,
that's
you have the
T.
T.
Okay.
Yeah,
And then there's a two cell. Sorry, and that's okay. And
like
sorry,
down
that's
on
all we're using
limit.
for now.
Yeah,
Yep. Um, okay. Okay. Oh, right. Okay. Sorry. No, there's this two cell eta, which goes from identity
here.
on plus
Yeah,
into that, right? Which you
yeah.
wrote over here. And this is maybe telling us that we want to. So the fact that we've got this eta from identity plus to UF is maybe telling us that we want to take an inserter of this diagram. Is that what's
Um,
or I mean, so I do understand. And then there's some other diagram, like we've got t squared. Um, oh no, okay, sorry.
I think yeah, something
Sorry,
like
sorry, sorry. No, I'm completely wrong. Because right, we want an inserter for this
yeah,
diagram.
like
Okay.
that.
Oh, and we already have this two cell, which goes identity. Ah, okay. So we're going to get like, sorry, sorry. We've got this
No, it's
picture here,
okay.
and then we've also got
Yeah,
this thing, equality, and this two cell comes from the image of eta, and then we'll like equify, um, and then we'll get like two different. two cells. One is like A after eta um, from I into A, and the other one is just like the identity on this morphism here, and then we need to do an equifier to get the equations. Okay, sorry.
Exactly.
Yeah.
So yeah, that's what I would like to say
Oh, okay.
next. Yeah, so after having the structure morphisms, that's not the end of the story because we need the unitality. That's what you are just you here is something like here, and also the multiplication.
Mhm.
And so we are going to take like let's say like one and two, two equivalents in
Right.
order to impose the two conditions. And the end product is exactly TH, the
Right.
Eilenberg
Okay.
object. So this is the ordinary categorical case, but in the infinity, oh,
Oh, there we go.
okay.
Okay.
Oh,
Sorry.
no, it's my problem.
Okay.
Yeah,
Yeah, no,
yeah.
that'll happen sometimes.
Yeah. So in the infinity categorical case, this should not be the end. We should expect that there is something here which is the inductive limit, like of
Ah,
this countable chain is a very long chain.
so and is it like so we've got one inserter, we've got two equifiers for the two equations,
Yeah,
but is the idea that in the infinity case those don't hold on the node? Like there's also um uh, uh, ooh. So is the idea that these equifiers aren't actually equifiers? Okay.
exactly. Yeah, we're considering like isomorphisms between things you want to hold. So they are not identities
Right.
anymore.
These equifiers are like inserting three cells. Okay.
Exactly. Yeah.
Okay, and then you insert four cells for the coherence. Okay,
Yeah.
cool.
So this is the Eilenberg-Moore object. It's the limit of the countable chain
hmm
of these inserters.
Okay,
Yeah, that's
cool.
the idea.
hmm
Okay. So what's next? Okay, so well, so this result is nice,
hmm
and we would like to know, uh, first of all, okay, yeah,
hmm
like how about other models, like apart from quasi-categories? So
Right.
quasi-categories are one particular model for
hmm
infinity one categories. There can be more, like
Right.
Seagull spaces.
hmm
And also, what about other limits? So
Right.
this is just for Eilenberg-Moore objects, and we'd like to know, like, is there any more that are if one of the lake
hmm
is not structure preserving,
Oh,
like this one, then will we still have the limits?
okay. So if T, which does not preserve J limits. Sorry, if one of these is not structure preserving. Oh,
Which
okay.
this one? Yes.
Oh, okay. So one
Yeah.
thing we haven't talked about is so this is just the construction of the Eilenberg-Moore object, and there's a claim that this thing
Yeah.
has all limits. So this thing will be a quasi
Category
category
with J-shaped limits.
with
That's
J-shaped
what
limits.
they have shown. Yeah.
Okay. Okay. So it's a quasi category with J-shaped limits, and they've shown that. Okay. We haven't seen that that's true, but we're posing other questions now. So other models. So right. Okay. So is the question like if you replace quasi-cat with some other simplicial category of models, is it always going to be a simplicial category of models that we look at?
Yes, indeed, for this
Oh,
uh,
okay. Okay.
for this question, we would like to take an infinity cosmological approach.
Okay.
Yeah, where
Okay.
we
You'll
would
have to.
like to replace QCat by an arbitrary infinity cosmos K.
Okay.
Yeah, which is, well, this theory is also developed by Hill and Faraday.
Okay. Okay. How about other models and other limits? Okay. So here we talked about arbitrary J limits, where J is a simplicial set. And what sorts of other limits um, would you consider? Um,
Yeah, so indeed, we would consider an infinity categorical analog of entities
okay.
and equivalents.
Okay.
Yeah,
Right.
they should be there.
hmm
Yeah, because that's how another makeable object can be built from. So we
Right.
more fundamental. It
Mhm.
would be nice if they are really there.
Okay. So these are limits, right? You're taking inserters and equifiers, or
Okay.
these are like higher dimensional inserters and equifiers. But there's also these limits. Um, so when you're saying
Uh-huh.
your question is what about other limits? Is the question like what
Yeah.
limits to take here?
Yeah.
What J? Okay,
No,
okay,
no,
cool.
not shaped limits.
Ah, okay, okay. So we're asking whether we can like extend this. So this is a theorem for quasi-categories, and is the idea to like maybe change quasi-category with some other model
Model.
for infinity one
Yeah.
category, and um uh and and is it to ask whether we can build up the Eilenberg Moore object by a
Yeah.
sequence of, other limits?
Yeah,
Is that sort of the idea?
exactly.
Okay,
Yeah.
cool.
Yeah.
Okay.
Yes. And so as I have just mentioned, we would like to make use of infinity Cosmo,
hmm
a theory developed also by Hugh and Verity. So the idea of their theory is to understand and study infinity one categories via a more model independent approach. So let me briefly tell you what an infinity cosmos is.
Okay.
So an infinity cosmos, K, so it is a quasi-categorically enriched,
Okay.
and it has zero nice things that we would like to have. For instance, the terminal objects
Okay.
and products. And also, we would like to say that there is a collection of maps which we would call isovibrations.
Okay. And so ISO vibration means something in like as maps between categories, but here it's just like a primitive notion.
Yes,
Okay.
yeah, it's just a name here, just a collection of maps, special maps.
Yeah.
Yeah, and of course, they have proved that it turns out that this collection can coincide with a
Right.
usual,
Okay.
yeah,
That's a good name. But okay.
yeah. And also, so K has terminal objects, products, and also pullbacks along isovibrations.
Ah, okay. So
So
if I,
by a
yeah.
double hit,
hmm
I mean an isobvibration.
Okay.
So that's a notation.
So I can pull if I've got any ISO vibration, I can pull back any morphism along an ISO
Yeah.
vibration, and if I pull back an ISO vibration along any morphism, it'll be an ISO vibration again.
Yes,
Okay.
exactly. And also, it has limits of countable chains of isovibrations. So if all of these are isovibrations, then the inductive limit exists.
Okay.
And also, K has simplicial powers. So for a random simplicial set J,
hmm
the power of A by J exists in K. If A is, well, let's use X, or maybe, yeah,
Okay.
not to be confused with the above A. So X is just an object in K.
hmm Okay, so it has some pleacial powers. So that makes, so in any V category, I can talk about having powers by objects in V. Um, So here we've got a quasi-category category,
Yeah, but J might not be
a
a quasi,
quasi-category.
yeah, just a simplicial set.
Okay,
But we would like it to, like this power to be in K.
right. Okay.
Yeah.
I guess any a quasi-category is a full sub. So is it the case that any quasi-category category is a simplicial category, right? Because I got this,
Yeah.
inclusion of quasi-categories into simplicial
Yeah.
sets,
Yeah.
and therefore I can also think of my K as being a simplicial category.
Yes,
And then, okay,
exactly.
okay, cool.
Yeah.
Okay, so it's like a simplicial category whose Hom simplicial sets happen to be quasi-categories or
Yes,
something. Okay.
exactly. Yeah. And also the collections of isofibrations contains all the isomorphisms.
Okay.
And also all the maps whose codomain is the terminal object.
Okay.
And also the isofibrations have to be closed under composition
Mm-hmm.
and products and lots of different limits.
Mm-hmm.
Yeah,
Okay. Close on
several.
the okay.
Yeah. And also one last thing, if I remember correctly, if F is an isobvibration in K, then we need uh, F lower star, which is this one, to be really an isobvibration in QCAT.
Okay. So there's an actual notion of isovibration of quasi-categories, which probably looks like isovibration of ordinary categories. And okay, so these are like representatively isovibrations as well as
Yeah.
okay, okay. Cool.
And yeah, examples would be great. So quasi categories with limits
Mhm.
and the limits preserving maps together form an infinity cosmos.
Right. Where J is any
Any simplicial set, like you can just ignore it.
oh okay.
Yeah,
So
yeah, just ignore it.
so it's got so like these are co complete quasi categories and continuous maps sort of.
Yeah,
Okay. Okay. Okay.
yeah. And also categories, because an ordinary one category can be viewed as an infinity one category
Yeah.
where everything is above its identity.
Mm-hmm.
So categories and functors together also form an infinity cosmos.
Mm-hmm. If I just take quasi categories without the limit.
It's also okay.
Okay, okay.
Yeah. So they philosophy behind is that an infinity cosmos capture infinity one categories with structure together with the pseudomorphisms between them, the structure
Okay.
preserving. If you don't have structure, then it's fine. I mean,
Okay.
yeah,
But okay.
yeah, yeah, yeah.
Okay.
And
Those are good examples. Um,
yes, so we would like to use infinity cosmos to do something.
mm-hmm.
But before that, there's still a long story, like how do we
Mm-hmm.
approach the problem?
Yeah. So I got one other
Okay.
question. So what about so I can view cats as quasi categories and uh what about like just set? Is set an infinity cosmos?
No,
Okay.
no.
Interesting. Okay.
You have to be like infinity one categories. Like
Right.
so, for example, simplicial sets, no, no. You
Okay.
have to be actually you have to be five-inch object for a
Oh.
model structure, reference
Okay.
object.
Right. So
Yeah,
if
for
I
cats we have I
oh
think we
okay.
have yeah.
Okay. But even if I think of like set, so I can think of sets as quasi categories which are just like discrete.
Okay.
But that's still not good enough. There's
Yeah.
some other condition that category, enriching category doesn't have. Okay, interesting.
Okay. No, wait. Oh, sorry. I think might be yes. For set, not for simplicial set, but
Oh,
for
okay, okay.
set.
Right.
Be
Simplicial sets doesn't behave
yeah,
like categories, but
yeah,
okay.
correct. Yeah,
Okay.
sorry. Okay.
It's just interesting to know if like,
Yeah.
so we're presumably going to talk about like categories enriched over some infinity cosmos. And it's not interesting to know if I can think of ordinary categories as an example, i.e. where K is the cosmos like set somehow.
Yeah.
Okay, cool.
Okay. So what's next? Okay. Next, I would like to talk about enhanced category theory.
Okay.
Because we will be using enhanced simplicial categories, a notion that will explain later.
Mhm.
So first of all, it's Lack and Schumann who developed the notions of enhanced two categories. Yeah, I think you have also heard of, well, you are very familiar with this notion indeed.
Yes, so so these are also called like F categories. Okay,
Exactly.
yeah.
Yeah, there are two names. Yeah, so roughly speaking, they are two categories with two types of morphisms, the tight ones and the loose ones. So what they would like to capture are two categories with the stronger and also the weaker notion of morphisms together. Yeah.
Mhm.
And examples, well, like for instance, ordinary one category with limits or, well, products maybe.
Mhm.
Yeah. And also the product preserving functors between them, which should be tight, taken as tight,
Mhm.
and also the usual functors.
Yeah. Okay, that's the lights. Okay, just 1 second while we turn it back on. Okay, cool. Okay, we're back. Okay,
Yeah, these are the loose maps.
okay, sure. And I sort of know, maybe we'll get to this, but like this is a special case of T algebras and
Yes,
I don't know.
exactly. So a more general example would be T algebras together with the strict T morphisms and the lax T morphisms. So the strict T morphisms could be taken as tight maps, and the lax T morphisms could be taken as loose.
Hmm. Right, I guess there's a few choices. You could do strict pseudo, pseudo-lag, pseudo-colag, but
Yeah,
yeah, that's it.
yeah,
Mm.
exactly. And also, uh,
Um,
okay, okay, thank you.
okay.
And why would they be interested?
Right,
Okay, why would they be interested in developing this notion? Is that Lack has previously worked out something, precisely limits for Lack's morphisms. So, well, first of all, maybe let's take a look at this example. Well, let me write it down. So, like, if we consider A, B, C to be monoidal categories, and let F be a lax, and also G be lax monoidal functor,
Hmm.
then let's consider the common object. of F and G, which looks like
Yeah.
this. So could this be equipped with a monoidal structure? Well, the answer is no here. Why? Because, well, we need to have something like this, the structure map, something like this.
Mm. The structure. Right. I think so if we like try if we just build this thing as a category, right, are we going to observe that the objects here are going to be like an A in a B in B, and a map FA into GB. Right. These are the objects of this category, right? And when we try to define a monoidal structure, if we want a map from um what's the
Like B1, B2, or maybe.
oh right, okay,
Yeah.
yeah. All right, we've got a pair of these things and we want to define the monoidal product.
Yeah.
So like FA prime V GB prime. Well, we want what's the idea is the product should be what F of A. Ah, okay. A.
Yeah.
So we might want to do A tensor A prime, G B tensor B prime, and then we need to build this map.
Yeah.
And okay, but if like we had, I don't know, a map, FA
Yes.
tensor like that. Okay, so maybe we want,
Yeah.
then we go, okay, okay, right.
Exactly. Yeah.
But in general, we don't have enough, if these are both Lax-monoidal, we don't have enough
We don't,
structure to
yeah,
define
we don't have the other direction going back.
them.
Yes, that's exactly this direction, what you have written.
Right.
Yeah,
So we did
we
have
only
that.
have
We could
this.
do U tensor V
Yes,
and then
exactly.
do the G monoidal
Yeah,
structure and get that.
yeah,
Okay. Okay.
yeah. Uh, so we see that, okay, this doesn't work when both of them are loose or lax monoidal. But if one of them just F
Hmm.
is monoidal, then it works. Because here you have this direction. And for there, you always have this direction for
Yeah, yeah,
elephant. No, sorry.
yeah.
Yeah.
Right. Okay.
So you see, just this, just F being tight suffices.
Hmm.
And this is also what Lack has been able to show. And he has shown that T arch L, which
Hmm.
means you take the last T morphisms, has those common objects whose domain is strict T
Right.
morphisms.
Okay. Yeah, yeah, yeah. Okay.
Yeah,
Hmm. Right. T alg lax. Okay, as long as the first thing is actually um, a strict morphism, i.e. a tight in this
yeah,
setting, then we can do this.
yeah. Even though this one G is not good. Yeah,
Right. Okay. And I'm guessing T alg colax has the opposite thing be
yeah,
true, right?
yeah,
Okay. Okay. That's that's quite interesting. Um, right. And I guess it's also true that these maps are going to be, are they both going to be tight maps or something? I'm
yeah.
thinking that,
That's what
yeah,
they
okay.
have shown that, yeah, the projections are also tight, which is very nice. And not only that, they LAC has shown that uh, they are how to tightness preserve reflecting.
Yeah, they
So
tighten detect tightness or
yeah,
something. Is
so
that right?
which means if you have okay, let's say this, you're not sure if this map,
Mm-hmm.
an arbitrary map from an arbitrary X, is tight or loose.
Mm-hmm.
But if you know that both of the compositions with the projections are tight, then this is automatically tight also.
Right.
Yeah.
Okay.
That's what he had shown.
Mm-hmm.
Yeah.
Okay. So what were we talking about? Okay, so Lax, there's this paper by Lack which looks at limits for Lax morphisms
Yeah,
and shows that you've got commas precisely when one
yeah,
of the edges is
yeah.
tight.
He has shown more, yeah, but this is one very good example
Mm-hmm.
discuss with.
Right, okay.
Yeah, and also this phenomenon has led Lack and Schumann to further develop the theory of enhanced two categories.
Right, okay. So I guess the point is that like this phenomena is like only observable once you've got this notion of like or like whenever you're working with T algebras, you sort of want to keep around these two different notions and be able to tell when a morphism is, the tight sort or the loose sort, and certain theorems are only true when you can distinguish between them.
Yeah, exactly.
Mhm. Okay. So you're going to tell us about enhanced infinity one category theory.
Yeah.
Okay.
Yeah, so we borrow the idea on enhanced two categories and we introduce the notion of enhanced simplicial categories. So roughly speaking, they are just simplicially enriched categories with two types of arrows.
Right, and now arrows are our zero cells of the simplicial hum sets or
Yes,
something. Okay.
so sometimes people do call them the zero arrows.
Ah, right, yeah,
Yeah,
okay.
yeah,
One cell's a zero arrows.
the
Okay.
simplex in the mapping space.
Right, okay.
Yeah,
Okay.
so we
Enhance
have
the
two
visualize.
types.
Sure.
Yeah,
Okay. Okay.
yeah. And so an example would be, so what we would like to describe, for instance, quasi-category with limits. Yeah, the objects.
Mm-hmm.
And the tight ones would then be the limits preserving maps between them.
Right, and the loose are just arbitrary maps of
Yes, yes,
quasi-categories.
yes, yeah,
Okay.
just maps.
Interesting. Now, I mean, maybe I should let you. Okay, so two questions come to mind, which we don't need to address now, but I know that like enhanced categories are also equivalently categories enriched over the category of fully faithful functors. Is that
Yes,
right?
so yeah, so maybe we can briefly discuss the formulations.
Okay,
Yeah,
okay.
actually, it might be, well, it is important because, well, I'm not sure if you have heard of like marked two categories or marked
So,
simplicial sets or
I think
yeah,
I've got the
marked.
idea. I mean, so I would have thought that marked is sort of to me, marked and enhanced are sort of the same thing. I get the impression
Yeah.
that marked, so probably there's this property that if I compose two tight arrows, I should get another tight arrow and identities should be
Yes,
tight and things like that.
yes, exactly.
Whereas maybe for marked that's not true, or I don't know.
That's true.
Oh, for marked as
So
well? Okay.
you're right that they are actually the same thing,
Okay.
but I would like to take this chance to promote our notion of enhanced two categories and also enhanced simplicial categories.
Mm-hmm.
It's because we are doing it with an enriched approach.
Okay.
Yes, so for marked two categories or marked anything, well, yes, they are the same. You have a special collection of morphisms closed under composition
Mm-hmm.
and closed under identities.
Yep.
But we cannot use enriched category theory to deal with them.
Right.
And the point of enhanced categories and stuff is that we can use the tools from enriched category theory,
Right.
which would be very powerful because they have a lot of things for us to use immediately.
Okay.
Yeah.
So is this like a philosophical distinction? Whereas like if I've got a two category and I just pick some random one cells,
Hmm.
sorry, some a closed class of one
Yeah.
cells, then I automatically get a I can from that recover an enrichment in fully faithful functors.
Yes.
But enhanced should mean for us enriched in some category and marked happens to coincide here, but it's a
Yeah,
different way of
yeah,
thinking
yeah.
about it. Okay.
So they are essentially talking about the same things.
Okay.
Yeah,
But they present the
the
data in different.
approach. Yeah,
Okay.
yeah,
Cool.
exactly. So for enhanced simplicial categories, so first of all, we consider simplicial sets, the category of simplicial sets, and the arrow category of it.
Hmm.
So roughly speaking, they are just the objects are just simplicial maps
Hmm.
between simplicial sets. And for the morphisms, you have commutative squares like this.
Hmm.
So which this means the arrow category of simplicial sets. And then there we denote by F delta, the full subcategory of this arrow category determined by the fully faithful and injective on objects simplicial maps. So
Right.
you take like this. Um, um, yes,
Fully
full
faithful,
embeddings.
injectable objects, completion maps. I see. Okay. So this is, um, and the idea is that like, if I want to define a fully faithful set, injectable objects completion map into T, I can sort of just pick a bunch of zero cells in T.
Vertices. Yeah.
Right. And then I guess I've got like T's, I don't know.
Yeah.
There's something like I got S0 and I take a pullback
Vertices.
or something.
Yeah.
And so I'll get, so in this way, I can think of such data as just like picking out, like marking some zero cells. But the nicer way to think about it is as a, a, a fully faithful injective on objects function.
Yes,
Okay,
exactly. Yeah. So it's just very similar as the formulation for enhanced two categories.
right.
So they have F, and I just added delta to me simplicial.
I see.
Yeah, so for them they use fully faithful and injective on object functors
Yeah,
between
that's okay.
categories. That's this very much the same thing.
Hmm.
Yeah, yeah. And then an enhanced simplicial categories is defined as an F delta enriched category,
Okay,
enriched
that's
in
a
F
nice
delta.
definition.
Yeah.
Okay.
Yes. So we have just talked about an example like quasi-categories with limits
Hmm.
and the tight morphisms, the tight zero arrows or the limits preserving
Yeah,
maps and loose are just the maps. Yeah,
right.
yes. And so for us, the interesting case is when the tight zero arrows altogether form an infinity cosmos, because that's what we would like to do.
The tight zero arrows form an infinity cosmos. Right, but the oh, okay, sorry.
Yeah.
So I've got um so as in okay, so I'm just looking at for now simplicial sorry, simplicial set enriched oh sorry, categories enriched in like simplicial sets. So like, I've got a category with objects A and B, and between them I've got some map of simplicial sets. So I've got like, I don't know, H tight, tau, mapping into, H lambda. So this is just a map of simplicial sets. And you're saying you're interested in such enriched categories where your tights land in an infinity one cosmos. Is that just saying I've got like S set, I
Hmm.
specify some like a sub class like, I don't know, C of simplicial sets, which forms an infinity cosmos, and I ask that all my H taus land in this subbit, or have I not understood?
Oh, so just take the above example, quasi-category with limits.
Yeah. Sorry.
So if you forget about the loose zero arrows, that's an infinity cosmos. So that's what I meant.
Oh, sorry. Oh,
Yeah,
I see, I
yeah,
see.
it's the mapping space
Oh,
itself.
sorry, sorry, sorry.
Yeah.
Sorry. Okay, let me try that again. So for any F delta cat, okay, so here's another definition of F categories is it's a functor between two categories, which is bijective on objects, locally injective, locally
Yeah.
fully faithful.
Yeah.
Okay. So it for any F delta category A, I've got like a I get this map A tau including into A lambda.
Yeah.
Right, and these are both just plain old simplicial categories.
Yes, in our case,
And I'm asking that this thing,
to be a cosmos.
okay, that thing's cosmos. Okay,
Yeah.
right, okay, and that example you gave above is
Yeah, because that's the interesting one we would like to do.
right.
Yeah, because we were trying to solve the problems
I see.
infinity one categories, and we would like to use the cosmological approach.
Right. So in saying that this thing, that like A tau is a cosmos, I have to give some extra data, don't I? I need to say what the isovibrations are. But will they just be isovibrations um, uh, of some, these are simplicial categories. No, in a general, yeah, okay. So
Yeah.
tell me about that.
Well, so indeed, I just get this. I mean, I just put this assumption when I proved theorem, and I don't deal with a new F delta, so that the things enriched in it is then enhanced simplicial categories whose tight part is in Cosmos. So I'm just mentioning this, yeah,
Okay,
to
okay,
tell you
okay.
that the interesting enhanced simplicial categories for was is always the one whose tight part is a Cosmos.
I see.
Yeah.
Okay.
Yeah, but this could be a very general concept. You can have enhanced simplicial categories whose tight part is not a Cosmos.
Okay. Light again. There we go. Okay. Okay. Um, okay, cool. This looks like a nice definition. I know a bit about enhanced categories, and I see that this is like a natural way to extend it to simplicial categories from two categories. Um, okay. Okay, cool. And there's this extra condition that we're asking for here, which is that, oh, you're just saying the interesting ones of these are those
Yeah,
where
for
your
what?
types.
Yeah,
Okay,
yeah.
cool. Okay. What next? So what was the context? So we talked about some of the things that Lack's done with and Lack and Chungwin have done with enhanced categories. Here we've now got a definition of enhanced simplicial category, and it's this nice sort of enriched. It's you
The
define it
setting,
just in terms
yeah,
of categories
yeah,
enriched over some other category, which is nice. You get a bunch of things for free.
yeah,
Like you can talk about a two category of, well, there's probably you can talk about at least a two category of these enhanced simplicial categories, but maybe it's even an enhanced simplicial category of enhanced simplicial categories or something. I don't know.
yeah.
Okay.
So now we have the setting to do things. And the next thing is that, so remember that I would like to explore all the limits other than Eilenberg-Moore objects. So we have discussed the inserters, the infinity categorical inserters. And so we would like to define this notion rigorously here. So we introduced the notion of rigged n inserters, which would capture the usual inserters. One is, I mean, the one inserters would be the usual inserters that we know in two category theory.
Right, yeah.
Yeah. And also it would capture a higher analog of equivalence. because as you have also mentioned, equifiers are just like inserters.
But
So you're like inserting
yeah.
something whose boundary is now made of two morphisms instead
Hmm.
of one morphism.
Right,
So,
yeah, yeah.
so the idea is like that.
I see.
Yeah.
Okay. And so something I'm expecting to come up here is that we're working in a enriched setting. We're defining a notion of limits.
Yes.
Now there's a natural notion of limits I can talk about when I'm
Weighted.
in, yes, weighted
Yeah.
limits.
Yes.
So,
Actually, this can be formulated as after the weight limit.
okay.
Um, but there is also an easier or more intuitive way to describe it. And
Right.
yet we are able to show that the two coincide.
Right. Okay. So this is maybe like so the Eilenberg-Moore object is also a weighted limit,
Yes,
but it's nice to have this very like
intuitive.
explicit construction. Yeah,
Yeah.
yeah. Okay. And I sort of know something about rigged limits, or I got this idea that rigged limits in general are special weighted limits where the weights are somehow are like coalgebras for some code. Though there might be a nice way of, I
Yeah,
don't know,
yeah.
this is
I
brilliant.
didn't know much, but yes, they are in the paper by Lack and Shulman.
Yeah,
Yeah.
yeah, okay. Okay, so maybe these are like special
Yeah, I
weighted
haven't
limits.
explored that.
Okay. Okay, so it's some F delta weighted limit, but you're going to give me a more
Intuitive
intuitive.
notion,
Yeah, okay.
way to describe it. Yeah. So like let S and T be two objects in, well, maybe just in an enhanced simplicial category. What do you like? What letter? Which is your
Oh,
favorite letter?
for an enhanced simplicial category.
Yeah, yeah.
I don't know enough about simplicial categories, but I would go with just like S A.
Okay, A.
That looks.
Yeah,
Oh, sure,
bolded.
that looks
Yeah,
good. Yeah.
bolded means enhanced.
Okay,
Yeah,
that
yeah.
makes sense.
Okay. And so suppose we have a loose, because
Hmm.
here is enhanced, we have loose zero arrow in A called D.
Sorry, there's
Yeah.
delta
Yeah, what does that mean?
boundary of the. Okay.
Yeah. Also, we have to assume that simplicial power exists in A.
Yes, that's
Otherwise,
right.
I cannot talk about this.
Simplicial powers exist in a. Okay, but
Assumption, that's an assumption.
okay, and that's so we said something before about the tight category being a
Cosmo.
cosmos in
Yeah.
which you already have
Yes,
simplicial
that's
powers. Okay,
hers. Yeah, yeah,
cool.
exactly. So what does that mean? Well, this,
And that's sorry, simplicial powers. So I mean, the natural notion of powers here is powers by arrows of. So
the thing you enrich in.
yeah,
Yeah.
so like where okay, because the thing I was wondering is if you've got a lambda, a tau, and a lambda, this whole thing together is enriched in F delta,
Yes.
but this thing here is just enriched in plain old
Yes.
S
Yeah,
det.
we are able to show that in a desirable case, this really exists in, I mean, in,
Sorry, this thing here. Oh, okay, okay.
for the interesting enhanced simplicial categories whose tight part is a cosmos. Yeah,
Okay,
yeah, we can show that
okay.
for the
So
specific case.
okay, I'm jumping ahead here, but like boundary of delta, is this meant to be like is this the object or is this the inclusion of this into uh so like I've got uh is so I've got the for any simplicial set oh sorry, for any n simplex, I've got a simplicial set which is its boundary
Mhm.
and I've got this inclusion. So this thing here, this is just the simplicial set which is the boundary of the
Yes,
n
we
simplex.
read
Okay.
it as a, well, coordinate simplicial set because actually F delta, the objects in F delta can be thought as enhanced simplicial sets.
Yes, okay,
Yeah,
okay.
you can just take everything, every vertex, everything to be typed of it.
Okay. And so that means that's like if I've got any simplicial set S, I can build an object in F delta by just taking the identity,
Yeah,
and this is the coordinate. Okay, cool. I
yeah,
understand. Okay.
yes. So what does they mean? Well, actually, we can think of it as picking a boundary inside the mapping space
Mm.
from F to T. So maybe some example would be great. So for instance, when n equals 1,
Mm-hmm.
then we what does that mean?
Okay. I so we've got del the boundary of one is just 2 points. So we've got two different maps from S into T. Is
Yes.
that the idea?
Yes, or maybe
And
you can make it wavy because this is wavy.
oh, okay,
Yeah.
these are wavy. So what tells me that they're um uh okay, so sorry, okay, right. This is oh okay. The waviness is I might take a second to figure this out. So this is a map from S into this thing
Hmm.
by the Kopow property is a map from this thing into okay. So
It's a
so
mapping
so
space.
this goes into the mapping. I see. So this I've got this mapping space on ST, and
Yeah.
this thing here is a F object of F delta. Is it?
No, it's a quasi-category. I mean, for well, a, a simplicial set,
It's a sim
an enhanced simplicial set.
This is an
Yeah.
enhanced simplicial set.
Yeah.
Okay, so I've got my so in principle there's two of these things. There's there's these tight and there's these
Yes.
looses.
Yeah, you're right.
However, on the left hand side, this is chordate. So if I want to, so what's the so a map from oh, but this is a loose.
Yes,
Okay, so
exactly.
there's loose maps between enhanced simplicial sets. F delta is an F delta category.
Yeah.
The loose maps are just the things downstairs, whereas the tight maps are commuting squares. Is
Yes,
that right?
exactly.
Okay, so
Yeah.
a loose map from this into this is the same thing as just a map between their underlying
Map.
simplicial categories, the loose ones.
Yeah.
And this thing is okay, which is why we've got these loose morphisms because this
Yes,
is the loose one.
exactly. Yeah,
Okay,
you
thank you.
it's perfect. Brilliant. Yeah, so this is so yeah, this is what D looks like
Mhm.
when n equals 1.
Okay,
And what about when n equals 2?
okay, this gets all.
Uh, no, it's not scared.
Okay.
So first of all, what is boundary of delta 2?
Well, yeah, so I think the boundary of delta 2, right, is
Yeah,
just
just
like
like a triangle.
an unfilled in
Yes,
triangle.
exactly.
So I'm expecting, I can't draw this very well, but I've got like,
Yeah, this be that this is three-dimensional.
okay, so I got something like this, presumably.
Yes, exactly.
And I want
Yes,
to, okay,
perfect.
okay, thank
Yes,
you.
yes. So yeah, and now to define a rect and etc., I'm making an assumption. Suppose that this map composing with the evaluation at the terminal vertex is tight in A, your favorite letter, A. Yes. Okay,
Okay.
what does that mean?
That means this bit's
Yes,
tight, right?
yes, yeah, yeah. I can
Okay.
like draw it like straight,
Okay, right. Okay, we use
like
straight
like
arrows.
this one.
Ah,
Yeah.
okay, okay.
Then we can define the rect and inserter, which we denote by ins, mean
Yep.
inserter of D, to be the pullback of D along the
Ah,
restriction.
okay. Right. Okay. Cool. So this is going to come with So like if I take this example to start off with, so here I've got my map D, which is defining this data here.
Yeah.
And now map upstairs
Mm-hmm.
is is going to involve a map. Now this is like a map here is the same thing as a map delta n into hom
One, yeah.
delta
Yeah,
one. In this case,
yeah,
it's delta
yeah,
one. You're
yeah.
right. Okay. Ins uh, one d. Okay, so there's a one here, and so this time. Oh, sorry, I got a loose. Now this restricts down to the same. So I've also got a map down here, don't I?
Yeah, exactly.
And if I restrict back along, okay, so like, okay, well, I'm gonna guess this is tight. That this one's tight and this one's allowed to be loose. For,
Yeah,
and I'm actually gonna get this morphism for this here.
yeah,
Okay,
which is very much the ordinary inserter.
right.
Yeah, and
And
if
this one
yeah,
is gonna, insert some three
yeah,
cell, which looks a little bit like an
equify.
equifier.
Yes,
Mm.
actually, if you take this thing to be like degenerate, to be like identity, then this collapses.
Right, and I've
And
just got my two
yeah,
cells and an okay.
yes,
And if this is like if T sort of like doesn't have enough high dimensional data, then a three
yeah,
cell, or like if all the three cells are degenerate, then this thing will just express equality or something between the two.
two morphisms, two
Right,
the
okay. Oh, that's very nice. So these are all these like equifiers and high dimensional things in this language are just high dimensional versions of these rigged inserters. So this is okay, so so this is loose. Are all of these maps tight?
yes.
Okay.
This is not. This I think is not.
Okay, that
Yeah,
feels
yeah, but
right. Yeah.
well, yeah, but we need some, well, to prove, to show.
Right.
Yeah.
Okay, but so that just says that this map can still be loose.
Yeah,
But this
the
bottom one
bottom one
probably
is
has to be
always
tight,
tight.
right? Because it
Yeah.
had a tight one here. Okay. So I'm interested about this. So before you talked about these commas and commas are not well, I suspect that if I can build commas, I can that's maybe relevant um,
Yeah.
to building. Well, okay, sorry, this is jumping ahead, but if I can build commas, I can
You
take A
can.
times C,
Yeah.
and then I've got these two cells, and I can maybe build. Sorry, if I can build inserters, and I got products, which I know I've got
Yes,
products,
exactly.
but
You can build commas.
okay, and you said that Lack had this result about, okay, you can only do this comma when this thing, one of these things was tight.
Yeah, one of these.
Okay,
Yeah.
and here we're seeing the same kind of thing. So there's a
Yeah.
supposition that one of these edges we're pulling back along
Yes,
is itself.
exactly. Yeah.
Okay.
So yeah, you see, it's just one of them. So here I'm using the terminatives.
Mm.
But if you would like to like flip the direction, you can also use the
Right,
in.
yeah,
It's
okay.
just like lax and collax. Yeah.
I see, I see. So there's okay. That's very nice. Um, Right, okay. So do you need this for some reason? Like, so you're defining rigged N inserters and okay, so the rigged, so if you've got this data D, that's the context in which you might ask for a rigged N inserter. You can take a pullback, um, but why do we have this condition that this map be um, tight. Is that really important somewhere?
Yes.
Okay.
Yes. So this is just like the two categorical example that we
Hmm.
discussed. We really need one of them to be tight
Um,
in order for the whole thing, the limits
mm,
to exist
right.
in an enhanced simplicial
Okay.
category.
So like Lack could define like there is still this notion of like an arbitrary comma object where you've just got two looses,
Hmm.
but the point is that in a very interesting example of an enhanced two category, namely Tialj, lacks,
Mm-hmm.
you just don't have these.
Yeah,
So is the point that like these in many like interesting examples, this condition is necessary for these inserters to exist.
yeah,
Okay.
yeah.
Right. Okay. Okay, that's quite cool. So we've talked, so we always have so we're talking about so I know like products, inserters, and equifiers are an interesting class of
Yeah.
limits, and that you've already covered inserters and equifiers. Um do okay, and products are just not interest like
Well,
easier to
it's
stop. Okay.
interesting.
Okay.
Yeah, but for our case, we are interested in the enhanced simplicial categories whose type part is a cosmos.
Okay.
And for a cosmos, products exist.
Okay. Ah, I see, I
So,
see.
yeah. So we immediately have that. We directly have it.
Right, okay, right. So if you've got if you've got your tight part as a cosmos, then you can automatically get tight products.
Yes, type product. Yeah.
Okay, okay. Cool.
Yeah. So
Okay.
yeah, so we have the pi
I
limits.
see. And
Yeah.
once you've got these pi limits, there are a bunch of other things you can build, like
A lot of
this. Yeah,
things,
yeah.
just like the usual monad theory.
I
Yeah.
see. Okay, that's very nice. And so this was stuff you've done in your thesis. Is this the project you're talking
Yeah.
about? Okay. That's very cool. So do you have this is a nice notion of enhanced limit. Do you have like examples of so we started off talking about algebra Eilenberg-Moore objects.
Yeah.
Um do so is there do you have a result about like constructing and Eilenberg-Moore objects, you gave a nice construction of them using a sequence of inserters and equifiers and so on. Is there, so now imagine I've got some enhanced to, enhanced simplicial category. What are they? Enhanced infinity,
Enhanced simplicial category.
enhanced simplicial category.
Yeah.
Okay. Um, then I are you about to tell me something about having a monad on an enhanced simplicial category and constructing its Eilenberg-Moore object
Yeah.
as a sequence of rigged limits? Okay.
Yeah, well,
Or is
well,
it more?
actually, they so in the paper by Hu and Therity,
Mhm.
they have built a chain, a countable chain, and then of what they call like projective weights,
Mhm.
and then they have shown that the limits of that chain is really the Eilenberg-Moore objects.
Mhm.
Yes, and for us, we note that we can describe all these in terms of rectangular sectors in
Okay.
enhanced simplicial
So
category.
this chain is like, in principle, it's this thing here.
Yes,
Right, and so they've
yes,
got some description of this chain whose limit is the Eilenberg-Moore object,
yes,
and you've now shown that every element of the chain is
yes,
itself a rigged.
yes,
Ah,
yes.
okay.
So yeah, indeed, there is a well, people define an element more object to be a weighted limit.
Hmm.
And then, so for the weight, they are able to express the weight, let's say this W.
Hmm. So
Okay,
where have you written
it's the weight for the Eilenberg-Moore objects. And they're able to put W as the limit of a countable chains of subweights
Ah,
of
okay.
something like, yeah. And I'm not sure, like, yeah,
I see.
yeah,
Okay, so this is okay. This
yeah,
feels familiar. Like you can sort of, it's the idea that you like you extract all this rather than starting with your monad and then building all these inserters, you like just build up one W, which is somehow a limit of this chain, and that W will like store, like compact everything into a single weight that you can then use to take any monad and
yeah,
yes, okay,
yeah, exactly.
weighted limit. Okay. Ah, okay, that's quite nice. Um, okay, we might have to stop soonish because we've been talking for a while. But
So that's also what I plan to discuss today. Yeah, I don't want to rush.
yeah,
Yeah.
okay. But I think there are more things that I think
We can
you
talk
can,
about
yeah, you could tell us
later.
about your thesis work,
Yes,
and I'd be
thank
very,
you.
very happy to hear more.
Thank you.
Okay.
Thank you, everyone.